Hey there, so what we're going to do today, we're going to start looking at gas volume calculations. So previous lesson we were looking at the mole volume. Today we're going to start looking at gas volume. Okay, so just a wee sort of note from before about the molar volume, about the whole concept of that. So from before, 1 mole of any gas, and you should know this, yeah, 1 mole of any gas, and obviously it's going to be at the same temperature and pressure. The same temperature and pressure. So 1 mole of any gas at the same temperature and pressure occupies the same volume. Occupies the same volume. Okay? Because that concept there sort of links into what we're about to learn. So this means we can match reacting moles to volumes, but, okay, this is the important part, but only if it's a gas. Okay, but only if it is a gas. So we're going to highlight it. Okay, that's the whole concept. It's gas volume we're looking at. So this means we can match reacting moles to volumes, but only if it's a gas. Okay, might not make sense just now, but it certainly will after this. So let's just say we've got the Haber process. So we've got nitrogen, 3 moles of hydrogen, and that's a reversible reaction, so that will give us 2 moles of ammonia. Okay? Now, every single one of these is a gas, so that's fine. And if we look at the number of moles, nitrogen, we've got 1 mole, hydrogen, we've got 3 moles, and ammonia, we have 2 moles. Yeah? Now, what this bit here means, we can match the reacting number of moles to the volumes. Now, because 1 mole of any gas at the same temperature and pressure occupies the same volume, if we've got 1 litre of nitrogen, that's 1 mole. 3 moles would mean we've got 3 litres. We've got 3 times what we've got for nitrogen. And then ammonia, because that's 2 moles, we must have 2 times, so that's going to be 2 litres. Okay, and that can work out for any volume. Let's just say we've got 10 centimetre cubed of ammonia. Yeah? Hydrogen, because we've got 3 times the number of moles, we must have 3 times the volume, so that's going to be 30 centimetre cubed. Ammonia, because we've got 2 times the number of moles, that would be 20 centimetre cubed. And again, that works for anything. Let's just change this number to 15 centimetre cubed. Let's say we've got 15 centimetre cubed of nitrogen. Hydrogen, because we've got 3 times that, yeah, 3 times 15, that would be 45 centimetre cubed. And ammonia, yeah, because that's 1 mole going to 2 moles, 15 times 2, that's going to be 30 centimetre cubed. Okay, that's what we mean by that, by us matching the reacting moles to the volumes. Okay, now a wee side note, I have already pretty much said it up here, it can only be a gas. Now for liquids and solids, this doesn't work. Okay, you ignore the volume. Okay, we cannot use the volume relationship with these. Okay, we can't use the volume relationship with solids and liquids. It only works for gases. Okay, so again, let's just say we've got this reaction, we've got carbon, the combustion of carbon, so we've got oxygen, that's going to give us carbon dioxide. Okay, now you'll notice that oxygen, carbon dioxide are the only gases here, Okay, so what that means, because that's not a gas, okay, that's a solid, not a gas, it doesn't work. Even though we've got 1 mole, yeah, 1 mole, 1 mole, 1 mole, it doesn't work, okay? So if we've got 1 litre of oxygen, we ignore the carbon, we've got 1 litre of carbon dioxide, yeah? If we've got 20 centimetre cubed of oxygen, we've got 20 centimetre cubed of carbon dioxide, and if we've got 3.5 centimetre cubed of oxygen, we've got 3.5 centimetre cubed of carbon dioxide, okay? And that's the basis of this. So, as we know, in most reactions, in fact pretty much them all, okay, as we know, in most reactions we will have an excess and limiting reagent. Okay, and you've done that before, we did it just recently, we did a wee consolidation lesson on it. You're going to have excess, and you're going to have a limiting, not reagent, sorry, a limiting reactant. Okay, now the same applies to gas volume, okay, so the same applies for gas volumes, and we will need this to work out the volume and composition of the resulting gas, mixture. Okay, again, this here might not make sense to you, you might not understand it, but you will when we start going over examples. Okay, so the same applies for gas volumes. We need this to work out the volume of composition of the resulting gas mixture. So we're going to do a wee bit of excess and limiting, but it's much easier. Okay, there's no really, you don't need to use any mole equations or anything like that. Okay, right, let's just go straight into the examples. That's the best way to learn these calculations, is just to do example after example after example. Okay, so we'll do 3 examples. So question 1, what volume of nitrogen dioxide is produced when 100 centimetre cubed of nitrogen is sparked in excess oxygen. Now, good thing about this question, we've already been told what the excess is. Okay, the excess is oxygen, which means the limiting must be nitrogen. But anyway, here's the equation. So we've got N2 plus 2 moles of O2 in the gaseous state, and that goes to 2 moles of NO3 NO2 in the gaseous state. Okay, so N2 goes to 2 moles of O2, N2 plus 2 moles of O2 goes to 2 moles of NO2. Now, as with every single question we do, the first thing you want to do is write what you know. So, what do we know? Well, if we read the question, we've got 100 centimetre cubed of nitrogen. And what we're trying to work out? We're trying to work out the volume of nitrogen dioxide. Okay? So, if we look at this, let's get our ratio between N2 and 2NO2. And it's a 1 to 2 mole ratio. Hopefully you can see that 1 to 2. Now, if we've got 100 centimetre cubed of nitrogen, because it's 1 to 2 and they're both gases, that must mean we've got 200 centimetre cubed of nitrogen dioxide. Okay, so that's our answer. Yeah, we have 200 centimetre cubed of NO2. And that's it. How easy is that? Yeah? Now, of course it gets harder. Always does. Always can. So question 2, 10 centimetre cubed of butane gas is mixed with 75 centimetre cubed of oxygen, and the mixture exploded. Okay? What I want you to do, or what we're going to do, is calculate the volume and composition. Now that's a key phrase, volume and composition. And it should trigger you to be doing this type of calculation of the resulting gas mixture. Okay, so these are the words you want to look out for. Calculate the volume and the composition of the resulting gas mixture. Okay, so if we do this, start here, so C4H10, that's our butane gas, add 6.5 moles of O2, and that goes to 4 moles of carbon dioxide plus 5 moles of H2O as a liquid. Okay? Now, move that on. Now, we should be looking at that. You should be noticing butane, it's a gas. Oxygen is a gas. Carbon dioxide is a gas. But water is a liquid. And because water's a liquid, score it out. Yeah, it's not a gas. This only works for gases. Okay, so we ignore the liquid altogether. Yeah? Now, let's do what we always do, and we write what we know. Okay? So, what do we know? We know our volume of butane is 10 centimetre cubed. Okay? We know our volume of oxygen is 75 centimetre cubed, and we're trying to work out the overall gas mixture. Now we need to include the excess as well, because we are going to have excess, yeah, but we need to work that out. So what you're going to do is you're going to work out, you're going to split your page into 3, just like we would an excess question. Okay, in the middle, mole ratio, and it's going to be the mole ratio between the 2 reactants, because it's excess limiting. Okay, so it's going to be C4H10 and O2, and that there is a 1 to 6.5. Hopefully you can see that, yeah, 1 to 6.5. Okay, so we have butane on the left and we've got oxygen on the right. Now this is easy, we don't need to do any calculation. The volume for butane is 10 centimetre cubed and the volume of oxygen is 75 centimetre cubed. Okay, now again with all excess questions, drag this in. So 10 centimetre cubed arrow needs, okay, needs, obviously say times that by 6.5, so 10 times 6.5 would be 65 centimetre cubed. Now, we just stop there. I know with excess we bring this in, we go back, but you only need this wee bit. So again, let's highlight this. This here is what we need, okay, and this one is what we have, okay. So as we do with all excess questions, highlight the one on the right and then the one on the far right. Yeah. Now we write our resentences. So we need 65 centimetre cubed of O2. Okay, I'll highlight that. Yeah, we have 75 centimetre cubed of O2. Okay. So, if we need 65, we have 75, that must mean oxygen is in excess by 10 centimetre cubed. Okay, hopefully you can see that oxygen is in excess by 10 centimetre cubed. Okay, which obviously means that C4H10 is the limiting. Okay, and it's always the limiting that we take forward. Okay, so we've got C4H10 and that goes to carbon dioxide. Yeah, we ignore the water, just carbon dioxide. And that, hopefully you see, is a mole ratio of 1:4. Now, butane, we have 10 centimetre cubed of butane. Okay, we've got 10 centimetre cubed. So if we've got 10 centimetre cubed, yeah, that gives us 40 centimetre cubed of carbon dioxide. So what that means, so we have a total of 50 centimetre cubed. Okay, 10 centimetre cubed is of the oxygen unreacted. Yeah, that's the excess oxygen that we've got. And then 40 centimetre cubed is coming from the carbon dioxide produced. Okay, and that's it. That's it. So, let's do another example. So this is going to be question number 3. This will be the last one. Okay. Question 3. I will call it 3A. We'll do 2 parts. Okay. So question 50 centimetre cubed of ethane. That's got the formula C2H2 is burned in 220 centimetre cubed of oxygen. Okay, and then the question, what will be the volume and composition of the resulting gas mixture? Okay, now there's those key words that should be triggering you to be like, right, okay, this is a gas volume question. So will be the volume and composition of the resulting gas mixture. Okay, so this is the equation here. Where are we? So C2H4 is a gas, add 3 moles of O2, and then that goes to 2 moles of CO2 and 2 H2O as a liquid. And again, very much like last time, because that's a liquid, we can score it out, yeah? Because it's not a gas. Yeah, it's not a gas, we're not interested in it. Okay, so let's write what we know. If we look at this, what do we know? Well, we know from the question we've got 50 centimetre cubed of ethane, so we write that. So always write what you know. 50 centimetre cubed of ethane, that's burned in 220 centimetre cubed of oxygen. Okay, and we're asked to calculate the resulting gas mixture. So we need to work out the volume of carbon dioxide and also what one of these two is in excess. Okay, so let's split our page like so, and mole ratio goes in the middle. Mole ratio between what? Between the two reactants, because it's limiting excess, and that is 1 to 3. Okay, so C2H4 on the left, oxygen on the right. So the volume is 50 for ethane, and the volume for oxygen is 220 centimetre cubed. Okay, bring it in, and what that means, 50 centimetre cubed needs, because it's a 1 to 3 ratio, times it by 3, it needs 150 centimetre cubed. Okay, now do the exact same, highlight. If you don't have a highlighter, that's fine, just circle it. So highlight or circle the one on the right and the one on the far right. So that's what we need, that's what we have. Okay, so let's write our wee sentences. We need 150 centimetre cubed of O2. We have 220 centimetre cubed of O2. So hopefully if we need 150, we have 220. Hopefully you're able to see oxygen is in excess of 70 centimetre cubed. Okay, and we can highlight that because that's the first part of the question. We've worked out how much excess we have. So that tells us we have C2H4 as the limiting. Okay, so of course we take that forward. Yeah, C2H4, we take that forward and we're trying to work out, don't need to work out this, just need to work out carbon dioxide. So that's 2 moles of CO2. So that is a 1 to 2 mole ratio, and C2H4, we have 50 centimetre cubed of it. Okay, and because it's a 1 to 2 ratio, that means carbon dioxide, we're getting 100 centimetre cubed. Okay, so what does that mean? So we have a total of 170 centimetre cubed of gas. Okay, 70 centimetre cubed of this is oxygen unreacted, is that excess oxygen. Okay, and then 100 centimetre cubed is from the CO2 produced. Okay, so 70 from the oxygen, and we're getting 100 from the carbon dioxide. So in total, that's 170. Okay, now there is a part B to this. So calculate the volume. Now, this is a great question, this. I absolutely love this question. Okay, calculate the volume. It's quite cheeky. So calculate the volume if reaction is repeated in a closed container. Okay, a closed container, and heated to 200 degree Celsius. Now, they'll do this, they don't do it very often, but they can do it. Okay, they can put a question in like this. So calculate the volume if reaction is repeated in a closed container and heated to 200 degrees Celsius. Now we have to think, you have to think, what happens at such a high temperature? Now if we look at a reaction, ethane, already a gas, oxygen, already a gas, carbon dioxide, already a gas, water, interesting. What's going to happen to water above 100 degrees Celsius? hopefully you've got it. It converts into a gas. Yeah, water boils at 100 degrees Celsius. It evaporates into a gas. Okay, and this is a trick question. So water turns to a gas at 100 degrees Celsius. Okay, so the total volume is going to be different because that's now a gas, so we need to include that in the resulting gas mixture. Okay, now, good thing is we've already done the hard work. We've already worked out that ethane, yeah, is the limiting reactant. So it's ethane going to 2 moles of water. Yeah, 2 moles of water. So we have 50 centimetre cubed of ethane. And because it's a 1 to 2 ratio, that means we're going to get 100 centimetre cubed of water. Now, from before, we had 170 centimetre cubed. Okay, and we would add that to our 100 centimetre cubed of water. So in total now, if the temperature was to take place at 200 degrees Celsius, because water evaporates at 100, in total, we're now going to have 270 centimetre cubed. Now, that is a great question. Doesn't come up very often, but just be aware, if we're heating above 100 degrees Celsius, water does, in fact, become a gas. Okay? So, just to sort of summarise what we've learned, as usual, you still need to know that whole bit from before, yeah? So 1 mole of any gas at the same temperature and pressure occupies the same volume, and that links into this, okay? So if we've got 1 mole and 3 moles, if we've got 1 litre, we times that by 3, that's 3 litres, okay? The number of moles will multiply the volume. If we've got 15 centimetre cubed, times it by 3, we've got 45, yeah? Very important, we can't include our solids and liquids, okay, because they're not gases, and this bit here only applies to gases, okay? Next part, again, simple calculations. Question 1, very straightforward. I'd be surprised if you got something like that, but again, that sort of introduces it. This question 2 and question 3 is more like something you're going to get. Okay, again, just set it up like you would a normal excess. It's easier because we don't need to work out the moles, etc. We can do this relatively quickly. Yeah, okay. Right, I'll put up some questions on Teams for us to try, but that is us for today, so thank you.